This screencast is on tension. Tension normally refers to the force in a string, or in a rope, or in a cable. So if you suspend something with a rope, then that rope exerts a force on the object it's holding. So if you're holding up a bucket at the end of the rope, there'll be a tension in that rope, or the force in the rope required to hold up the bucket. Before we get into tension though, I just want to do a few examples with elevators, because this is something students sometimes have trouble grasping. So if we take a look at an elevator, we have someone standing on a scale. Okay? So the weight of this person, they can judge by reading the scale. So in this case, the weight of the person is mass times gravity. So if you have a 70 kilogram person standing on a scale, then the scale has to push back with a normal force. And when the scale pushes back with a normal force, it also gives you a reading. And so for a 70 kilogram person, that reading would be 686 newtons. Now with this elevator, if you push the button and you have the elevator accelerate upward, you actually feel heavier in the elevator, because if you stand in the elevator and the elevator is pushing you up, you can feel it push against your feet. So normally you would have a weight and it'd feel constant if you're just standing in the elevator before it moves, and so as the elevator starts accelerating, it's exerting a force against you. So because it's exerting a force against you, then your weight will go up, and so the scale will actually read higher. There's a greater normal force required to keep you up. And so we can find out that force, or the net force from the scale, by the force of gravity needed to keep you up, plus the force needed to push you upward. So when an elevator accelerates up, then we can calculate the force of the scale, or the normal force, or the reading on the scale, by using this formula. If the elevator accelerates downward, that will be the opposite. So picture yourself standing in an elevator, you're standing on the scale, and then you push downward. The elevator is trying to accelerate down. It's accelerating away from your feet. Now it's not actually going away from your feet because the acceleration is not that high, but you can sort of imagine it as it's trying to pull away from your feet, and as it's trying to pull away from your feet aren't able to push down as hard on the scale, and since your feet can't push down as hard on the scale doesn't need to push upward as much, and so the reading of the scale will be less when you accelerate downward. So then the force that you'd feel would be force of gravity minus the force going down. And so we say mg minus a. So if we use an example of a 70 kilogram person in an elevator accelerating down at 2 meters per second squared, then to measure the scale, the force on the scale, let's say force of scale will be mass times gravity minus acceleration, 70 kilogram person times 9.8 minus 2, and so our force works out to 546 newtons. Also remember, if the cable holding up the elevator is cut, then the elevator will just fall. It's on free fall. And anything in free fall will be weightless. You may not notice weightlessness if someone is falling in the sky, for example, a parachuter, because you'll feel the air friction. but inside the elevator you wouldn't notice the air friction. So as the elevator falls, inside you would feel weightless and be able to float around there for a few seconds that you have left. So the next thing I'd like to cover is tension then in a string. If we look at a string in the bucket, so in the string there's a tension, and it's the force in the string. So if the bucket is just still and you're holding it up, the tension is mass times gravity. If you exert a force going upward and you pull it up, now you need an extra force, not only to keep the bucket where it is, but to actually pull upward. So when you do this, you're actually creating more tension in the string. And the tension pulling upward now becomes the tension required to keep the mass up plus the force required to accelerate upward. And so tension, when you're pulling upward, would be mass times gravity plus acceleration. Now if we do the opposite, if you have this rope with a bucket at the end, and now you accelerate your hand downward, when you accelerate towards the direction that gravity is going at, you'll actually find some slack in the string. So if you do it fast enough, you actually see the string go slack, and this means you're reducing tension in the string. So accelerating downward means that your tension will be mass times gravity minus acceleration. Now, many of the examples that you'll be doing are pulley systems. And so with a pulley system, the key, and as what we've been mentioning throughout the unit, this idea of net force becomes critically important here. To look at all the forces, draw them out, and figure out what are your net forces. Often you have to break things into components. If it's just something going straight down or horizontally, that's a bit easier. But if you have pulley systems on ramps, which a lot of them will be, you have to remember components and break things down and so on. So we look at this example. I have a mass here, which is 5 kilograms, and I'll call this mass B. And I have a mass here, and this is 9 kilograms. I'll call this mass A. And these two masses are attached by a string. Up on the top, there's a coefficient of friction of 0.21. And on the ramp, we'll say there's no friction. And this ramp has an angle of 25 degrees. So for this question, we'll say, what is the acceleration of mass B? So as I just mentioned, net force, very important. What are the forces acting on it? Well, there's one force that's going to make everything move. It's not the 5 kilogram mass. That won't move on its own. That will want to stay right there. So this 9 kilogram mass has gravity acting on it, but it can't go straight down because it's on the ramp. So what does happen is a parallel component coming from force or from gravity will pull it down the hill. And this force will cause a 9 kilogram mass to move and the 5 kilogram mass to move. Now just to complicate things, let's call it FP, sorry, to make this more consistent. Sorry, to complicate things, there is friction. So as you pull the 5 kilogram mass, there is a force resisting motion, and so that is force of friction. So our net force, I'm predicting this will move down, that the 9 kilogram mass will exert a greater force than the force of friction, and so I'm predicting this is going to go clockwise or down the hill. So the net force will be the parallel force coming from A minus, and resisting will be the force of friction coming from B. Now the parallel force coming from A will be mg sine theta, and you can look at the previous video that we looked at on net forces if you forgot how to do that, but it is breaking this down into components where you have force of gravity here, you have the parallel force, you have the normal force, and so on. And so we get mg sine theta gives us Fp, that component. So the force pulling down the hill will be approximately 37 newtons. And I'll just keep more numbers to keep things more accurate. The force of friction acting on B, the one that will oppose a motion, we know the force of friction is coefficient of friction times normal force acting on B. So that's 0.21. So we have the two forces, and to find the net force, and that will be my parallel force on A and my pen's not working too well here. So that's the net force, and so the acceleration, and remember that acceleration will be the same for both masses. They're attached by a string, so if you move one mass to the right, well, the second mass is going to have to go to the right as well because it's attached. The mass A is going to accelerate, then mass B will accelerate as well. So to find the acceleration of my system, of either mass, will be my net force, the force that's left over, divided by my total mass, because again, they're attached. You can't move one without the other. We have 26.989 divided by total mass of 14 kilograms, and that works out to 1.93 meters per second squared. And I will say downhill. Give some kind of direction, to the right, downhill, and so on. Now we'll do one more, make this one a little bit harder. If we have a pulley system, it looks a bit like that. It has two masses. This mass is 8 kilograms, call that B. This mass is 13 kilograms, call that A. And the coefficient of friction is 0. There's an angle of 40 degrees in this side of the triangle, an angle of 30 degrees. So, and my question is, what is the tension in the rope when these two masses are let go? So I'm going to start, and I'm going to guess that this is going to go clockwise. I'll say, well, 13 kilograms, not more than 8. The angle's not that different, so I'm going to assume 13 is going to win. There'll be times when it'll be difficult to guess which way it goes. It could be really close. And so let's just say I guess that the 8 kilogram mass would win. It would actually go that way. Whenever you guess wrong, it's actually not a problem. What you'll find is that your acceleration is negative. So if you guessed it was going down, and the acceleration is negative, well, turns out it was going up, and that's really the only thing. So as long as you catch that, is perfectly fine. So it's nothing to worry about. It does help for you to guess which way it's going to go so that you can set up the problem in that manner. So I'll start with net force, and I'll say, okay, net forces, this is going to move y. Well, I think it's going to move because the force acting on A, this parallel force acting on A, is going to pull it down. But I'm also saying that the other side, the parallel force acting on B, that will resist it. We'll try to resist motion. So my net force will be the force, parallel force on A minus parallel force on B. So let's take a look at what the actual forces are. The parallel force on A will be again mg sine theta. And notice the subscript MA, so the mass of A, that's where that came from. We have 13 kilograms, so 9.8 meters per second squared, times sine of 35 degrees. So that is 73.0736 newtons. The parallel force on B is mg, or mass of B, sine theta, 8 kilograms, 9.8 meters per second squared, sine of 40 degrees. And that's approximately 50 newtons. So, net force then. My net force is 73.076 minus 50.3945. My net force is 22.6791. So, if there is a net force, means there will be an acceleration. My acceleration will be my net force, the force is left over, divided by my total mass, 22.6791, divided by total mass 8 plus 13. And that is 1.07996 meters per second squared. Almost there. So I know that tension is the force in the rope. Tension is always caused by what you're dragging behind. So if you have two things like a train pulling one of the cars behind it, it could be someone dragging a person behind them. The tension's always caused by what you're dragging behind you, because if you cut the string so that you're no longer dragging the person behind you, there's no more tension. The tension's always caused by what you're dragging behind you. So in this case, it's the 13 kilogram mass going down. It's pulling the 8 kilogram mass up. And that means our tension will be mass B that's being pulled up times our acceleration. Now, since this is not on a flat surface, there's another complication. And that is, as I said, if it was just pulling on a flat surface, we have tension mass A. But it's not. It's at an angle. Before you even start to move the mass, there's already a tension in the rope, and it's caused by the parallel force of B. Now, if you start to pull upward with mass times acceleration, then you're going to add more tension. So the total tension in the rope will be mass B times acceleration plus the parallel force acting at B. And that is 8 kilograms. Is 1.07996 meters per second squared plus 50.3945, which is what we just calculated over here earlier, the parallel force acting on B, meaning the total tension in the rope is 59 newtons.